Suppose you had a box of Fruit Loops and wanted to know how many loops of each color were in the box. You could cut out each loop and record your data, but that would be a bit tedious. Instead, you could take samples from the box and determine a likely result from the data you collect. For this experiment, I poured one box of Fruit Loops into a bowl, took a handful of loops, counted the number of each color loop, and figured out the percentage of each color per handful. Then I replaced that handful and mixed it back into the bowl. I repeated this process 200 times and recorded the results. 200 may seem like an unreasonable number of trials, but a large number of trials is necessary to have confidence in the data you gather. As the number of measurements increases, many frequency distributions begin to resemble a bell-shaped curve or a normal distribution. The median or average value will be at the peak of the graph. From here, we need to find the margin of error of our data. The margin of error is found with this equation, where n stands for the number of trials that were completed. Our margin of error is approximately 0.0707. Now that we have our margin of error, we can construct a 95% confidence interval, or a range that we can be 95% confident contains the true population proportion. For our orange loops, we see that the median value is 26%. We add or subtract our margin of error and we find that this interval is 19% to 33%. Following the same pattern, we can see that the median percentage of yellow loops is 11%, which means that the 95% confidence interval is between 4 and 18%. The median value of purple loops is 17%. This means that the confidence interval is between 10 and 24%. Red loops have a median of 17%, so the confidence interval ranges from 10 to 24%. Blue loops have a median of 14%, which means that the confidence interval is from 7 to 21%. Finally, green also has a median of 14%, so the confidence interval is again from 7 to 21%. Another way to show the range and spread of data is with a box and whisker plot. A box and whisker plot shows the 5 key values needed to interpret a range of data. The low value, the lower quartile, which is the median of the lower half of the data, the median, the upper quartile, the median of the upper half of the data, and the high value. Data points that are more than 1.5 times the upper quartile or below the lower quartile are labeled outliers and are indicated as a dot on the graph. The box and whisker chart for the percentage of orange loops per handful has a low value of 15%, lower quartile of 23%, median of 26%, higher quartile of 30%, and a high value of 40%. The yellow loops have a low value of 5%, lower quartile 9%, median of 11%, higher quartile of 14%, and a high value of 20%. The purple loops have a low value of 7%, lower quartile 14%, median 17%, higher quartile 19%, and a high value of 28%. The red loops have a low value of 7%, lower quartile 14%, median 17%, higher quartile 20%, and a high value of 30%. The blue loops have a low value of 4%, lower quartile of 11%, median of 14%, higher quartile of 16%, and a high value of 24%. The green loops have a low value of 6%, lower quartile of 12%, median of 14%, higher quartile of 17%, and a high value of 24%. From this information, we can make educated guesses about the percentage of each color in our box of Fruit Loops. But how does the information gathered from one box relate to a much larger sample size? A nationwide study was done where 292 schools participated in sampling 506,702 loops. They found that the sampled loops were split 21% orange, 16% yellow, 15% purple, 18% red, 15% blue, and 15% green. My findings differ by a few percentage points in each color category. However, the total from the larger study all fall within the margin of error that was found earlier for each color. This means that the percentage of each color per box is approximately the same when the sample size is increased to multiple boxes.
Created using Powtoon.